Now, every time that we calculate a statistic, especially if we want to use it as an estimator for a population parameter, we've got to understand that there is some sampling error. This means that depending on the specific sample that we generate, the statistic we take could vary. If we got a sample which had a spread of the values in the population, would have a really good statistic or estimate of the population parameter. But what happens if we manage to get lots of values that were actually at the top end, lots of large values in the population for our sample? Through no fault of our own, we've actually generated a sample which has lots of large values in it. So the mean that we get, our sample mean, isn't actually going to be a good indicator of the population mean. Because of this, we often calculate a confidence interval, which is a range of values, an interval of values within which we think the parameter might lie. But we do have a percentage, a probability attached to that interval. This probability isn't the probability that the parameter is in the interval. It's actually the probability that if I took a random sample and generated this interval, it would contain the population parameter. So slightly different, and there is a nuance to the difference between these two things. So for example, here we have 4 confidence intervals that have been calculated from 4 different samples. Each of the samples gave us a different mean, and then when we created the interval around it, the buffer around it, majority of the time it would actually contain the real value of mu. You can see that from the first, second and fourth. Even though we had different samples, all of these do contain the mean. However, there is a chance that the sample we took generates a mean value, an x-bar value, that even when we create an interval around it, that interval does not contain the population parameter mu. So just be aware that that can happen. The levels of confidence that we usually calculate around are 90%, 95%, and potentially 99%. Obviously, the examiner, the question, the context can all decide that we might need to have a different level for the confidence interval. The central limit theorem states that regardless the distribution of the original population, we can expect our means, our x-bars, to be distributed normally. Because of that, the variables involved in calculating the confidence interval are going to be a normal distribution z-score, sigma for the distribution itself, and n as in the sample size. These are the parameters that will affect the width confidence interval. The confidence interval is going to be the z-score multiplied by sigma over root n. Hopefully you recognize this as the standard error, and that will be added above and below x-bar for that particular sample, meaning that the width is twice this size. I've started with x-bar following this normal distribution because we know by the central limit theorem that x-bar is going to follow a distribution that has the same mean but a standard deviation of sigma over root n. Our 95% confidence interval is going to use the z-scores that represent 2.5% in the right tail and 2.5% in the left tail. On the calculators or in the formula book or from memory, we know that that z-score is 1.96 and negative 1.96. Our standardization formula, since we're thinking of the sampling distribution of the mean, the denominator is sigma over root n. So let's just bear that in mind. So we'll start our probability statement. So the probability that a z-score is in between negative 1.96 and positive 1.96 should be 95%. We've set that up on purpose. Using the standardization formula, the appropriate standardization formula, and substituting into this statement, we can then start to work on manipulating this expression. We're interested in the inequality statement inside the probability statement. So we'll just focus on that, and we can start to manipulate to make mu the subject. So the first thing that I'll do is multiply everything by -1. Just want to make mu positive to begin with. So this expression actually goes to the right-hand side when we've made it positive. The middle term becomes mu minus x bar, and the right-hand side becomes -1.96 sigma over root n. Okay, the only other thing to do to isolate mu is to add x bar to each side. And this expression that we're left with is the confidence interval for mu, a 95% confidence interval for mu. This interval can vary based on the value of x bar that's calculated, but 95% of the time, the x bar value is going to help to generate a confidence interval. It's going to help to generate an interval which will contain mu. There's multiple ways we can represent this confidence interval, an x bar plus or minus. We can also just actually put in the confidence limits. So that's the lower and upper values. And we can use this square bracket notation once again to show those upper and lower boundary limits. And finally, just to formalize, we can actually just have an inequality statement with mu or the appropriate parameter in the middle. Okay, so either of these four are acceptable forms of a confidence interval. Since the last example worked in terms of unknown variables, let's go ahead and do a contextualized example. The breaking strain of reels of string produced at a certain factory have a standard deviation of 1.5. So sigma equals 1.5. A sample of 100, n equals 100, and we're told that the mean is 5.3. So I'm going to put all of those into the sampling distribution of the mean, which can be simplified in terms of its standard deviation, and even one step further. So I get 0.15 squared. Either of these forms of the x-bar distribution are valid. Just if you have a chance to simplify, I recommend that you do. Okay, so we're looking for the 95% confidence interval. So the confidence interval, x bar plus or minus z sigma over root n. We need to choose that correct z score, the z score that matches up with 2.5%. This can be found in the tables, this can be found from your calculator. Okay, and then just substituting in our x bar and our standard deviation. We then get the limits for the distribution: 5.006, 5.594. Okay, don't forget these can be represented as an interval. Next, we're told that the manufacturer becomes concerned if the 95% confidence limit falls below 5. A different sample of size 80 had a mean of 5.31. Will the manufacturer be concerned? So substituting in these values, we're really looking at the lower end of the confidence interval, and we get 4.98 and 5.64. Well, the 4.98 is below the 5 kilograms. So actually the manager is going to have, or the manufacturer is going to have reason to be concerned. Okay, so calculating confidence intervals, getting the form correct and substituting into it. I do want to point out that we weren't told that the original distribution was a normal distribution, so we have used the central limit theorem here, and the central limit theorem for the x bar allows us to then work with the normal distribution from there on in. Okay, just bear that in mind. Always just think to yourself, am I using the central limit theorem or not? So I'm just going to summarize the information from the question. Random sample of size 25, so n equals 25, is taken from a normal population with standard deviation 2.5 and a mean of 17.8. So that's sigma of 2.5 and x bar 17.8. And just to clarify, or just to raise your awareness, we know that the original distribution was a normal distribution. So we're not actually using the central limit theorem here. Because it was a normal distribution, we would expect the sample to follow a normal distribution. The central limit theorem says that regardless of the original distribution, it will be a normal distribution for x bar. And at this point, we substitute the values in. If there's a sensible chance and opportunity to simplify, we'll go ahead and do that. And I can see from these values, I should get 0.5 for my standard deviation. Okay, so let's actually look at the confidence interval. It's going to be x bar plus or minus the appropriate z-score, sigma over root n. X bar was 17.8. The z-score, well, we want a 99% confidence interval, so I want the z-score for 0.5%. So this z-score, we're either going to pull from the tables, or you can use the inverse function on your calculator. So obviously, 1% is going to be in the tails, and if we split that in two, that gives us 0.5%, which is the z-score 2.5758. So if we go ahead and we multiply by the standard deviation of x bar, we'll get the two limits that we're looking for, 16.51 and 19.09. And once again, there's multiple forms that you can display your confidence interval. In part B of the question, we're asked what size would we need, what size of sample would we need so that we've got a 99% confidence interval with a width of at most 1.5. So the width of this confidence interval is going to be 2 times z sigma over root n. And I've made the inequality so that it's less than 1.5. So just substituting in the appropriate values. N is the unknown that we're looking for. So we're just going to rearrange to make n the subject. Just be really careful with your rearranging. I like to bring some of these numbers together first. So 12.879. I have that all over root n. Well, that's less than a 1.5. All right, and from here it's a bit easier to do my manipulation. I'm going to divide the right-hand side by 12.879. And then I just need the reciprocal. So there's a few ways to think this through, but ultimately we get root n is larger than the reciprocal of the right-hand side. So 73.719 is less than n. That's what I get when I square. So we're going to need a sample size of 74 to make sure our 99% confidence interval has a width of at most 1.5. Okay, in part C, what confidence level would be associated with the interval based on the above sample of 25, but of width 1.5? Okay, so now that I know the width is 1.5, I'm going to start again with the expression for the width, and we're trying to find the confidence interval which is related to the z-score. So this time around, we know n, it's z that we don't know. So some smart rearranging, collecting some of these parts together. I could just divide across by this whole fraction, but the fraction actually equals 1. So z must equal 1.5. If the z-score is 1.5, what's the probability attached to it? All right, so be careful to track whether you're thinking of z-scores or probabilities. So a z-score of 1.5, you can pull out your calculators and just check what's the probability above a z-score of 1.5. Okay, and that probability is 0.0668. And since we have that in both tails, we have 13.36% on the external tails, well, in the tails. So the internal percentage, the internal area, the area between -1 and +1 is 86.6. And that is our confidence level. All right, just be clear on the steps that you're taking as you make your way through that. The examiner will design the questions to test that you actually know what we're doing with the confidence interval, rather than just you are familiar with a formula.